Welcome, everyone. Today, we'll dive into the fascinating world of the two-sum problem and explore an efficient strategy to solve it in just one pass. Every time you total prices in a shopping cart or combine scores in a game, you are quietly solving little search puzzles about which numbers add up to a target. Today, we are going to unpack a famous version of this called the two-sum problem, which shows up constantly in coding interviews and real systems. We will build everything from simple familiar ideas, first the problem story, then a slow but obvious solution, and finally a faster pattern that just uses a basic dictionary like you have seen in Python.
So by the end, I should understand not just how to solve two-sum, but also why the fast version is better than the obvious one, right?
Exactly. We will connect the everyday story to a precise problem, compare two solution styles, and you will leave with a mental template you can reuse on many similar interview questions. Imagine you have a list of item prices and a fixed amount of money, and you want to know whether you can buy exactly 2 items without going over your budget. We turn that story into a question about a list of numbers and a target total, asking whether some pair in the list adds up exactly to that target.
So it is not about adding everything, just about finding one matching pair that hits the target?
We will first look at the most straightforward way to search for a pair, and then we will see how a simple pattern using memory lets us speed things up a lot. Our focus will be on understanding the setup and the reasoning so that when you later see or write the code, it will feel like an obvious translation rather than a memorized trick. Let us now turn the shopping story into a clean math-like statement that a computer can work with.
I think I know the idea informally, but I want to be precise about what the input and output look like.
The input is a list of whole numbers, which we call an array of length n, and a separate number t that is the target sum we care about. The output we want is positions in the array, usually called indices I and j, such that the numbers stored at those positions add up to the target t.
So the answer is really about positions, not just the values themselves, because the same value could appear more than once.
There is also a natural rule. We are not allowed to use the same position twice, so the two indices must be different entries in the array. The most direct idea is to try every possible pair of positions I and j, add their values, and see if any combination hits the target.
That sounds simple to code, but I guess it might be slow if the array is large.
This big O of n squared expression captures the cost of checking all pairs. If you double the array length, the number of pairs roughly quadruples.
So we want to avoid that n-squared growth and somehow get closer to linear time instead.
To beat the slow all pairs method, we need to avoid repeating the same work and reuse information from earlier in the array.
That sounds like a place where storing some extra data, like in a dictionary, might help.
At each position, we see some value x, and we know that the only way it helps is if we can find another value equal to t minus x. We can keep a hash map or dictionary where each key is a value we have already seen, and the stored data is the index where it appeared.
So the map is like a memory of earlier values, ready to answer membership questions quickly.
When we reach a new value x, we immediately ask the map if it has the needed partner t minus x already stored from some earlier position. If the partner is in the map, we already know the index of that partner, and we are currently at x, so together they form our answer, and we can stop early.
And if the partner is not there yet, we just add x and its index to the map and keep going.
Because we only scan the array once, and each map lookup is fast, on average, the total work grows in big O of n linearly with the array length. Because we only scan the array once, and each map lookup is fast, On average, the total work grows in big O of n linearly with the array length. Let us see the map idea in action on a small concrete example so the flow feels natural.
Walking through one example slowly usually helps me remember what each step is doing.
We will use the class example with numbers 2, 7, 11, and 15 and a target of 9. At the start, the map is empty. We read the first value 2, see that its partner 7 is not there, and store the pair of value 2 and index 0. Next, we read 7 compute that the needed partner is 2 and find that 2 is already in the map at index 0, so together they form the correct pair.
So we do not even need to look at 11 or 15 because we can stop as soon as we find the first valid pair.
If we ever finish scanning the entire array without finding a partner, we return some special result, like a pair of negative ones, to signal that no solution exists. Now that the example feels clear, we can compress the idea into a short language agnostic algorithm.
I want to picture these steps so that writing actual code later is just a direct translation.
First, create an empty map that will remember which values we have seen and at which indices they appeared. Then loop over indices from 0 up to n-1. At each index, I look at the current value, compute the partner you would need, and check whether that partner is already in the map. If the partner is there, you know both indices I for the current value and j for the stored one, and that is your answer. If not, you add the current value and its index into the map and move on.
So the map is always one step behind, holding only values from earlier positions, which guarantees the indices will be different.
Finally, if you reach the end of the loop with no match, you return whatever your language or problem specification uses to signal that there is no solution. Let us step back and measure how good this algorithm really is in terms of time and space.
I know the map method feels faster than checking all pairs, but I want to connect that to big O notation.
For time, we visit each element of the array once, and each map lookup or insert is fast on average, so the running time grows in big O of n. For space, in the worst case, we might store almost every element in the map, so the extra memory we use also grows in big O of n. Linear time means that if you double the number of elements, you roughly double the amount of work, which is far better than the quadratic growth of the naive method. The cost we pay is extra memory to hold the map, which can grow to one entry for nearly every value in the array.
So we are trading memory for speed, which is often a good deal when memory is cheap and time is expensive.
In summary, the map lets us avoid considering all possible n-squared pairs explicitly, while still guaranteeing we find a matching pair if one exists. In summary, the map lets us avoid considering all possible n-squared pairs explicitly, while still guaranteeing we find a matching pair if one exists. To finish, let us do a quick practice problem and the reflection so you can test your understanding.
I will try to run the map method in my head and see if I can find the pair and explain why it is fast.
Try to scan the array from left to right. First, you see 1, then 3, then 4, then 2, updating the map each time, and checking for the needed partner.
Starting from the left, I would eventually reach the value 2 and realize I need a 4, which I saw earlier, so the zero-based indices would be 2 and 3.
Exactly. The pair 4 and 2 make 6. So indices 2 and 3 in zero-based indexing form a valid two-sum answer here. Think about why we never need to restart a scan. Every time we move forward, the map already contains all earlier values. So in a single pass, we can detect any matching partner we need.
That makes sense. Each new element is compared only to the compact memory in the map, not to every later element, which is what saves us from the slow all pairs search.
Thanks for watching this. Subscribe to Thinking in Math channel for this and other interesting math topics. And We always welcome your feedbacks. Leave your questions and suggestions in the comments.